So welcome to Mime 380, Modeling and Control of Engineering Systems, Summer 2017. My name is Mohammed Alahinia. I teach in the Mechanical Engineering Department. And the course really has two subjects. It has, as the name suggests, it has the modeling section, which would be the focus for the first part of the course, and it has the control section, which would be the focus after the midterm exam. I have already posted the class syllabus as well as the schedule, and I also emailed you ahead of time because Blackboard is not available until the actual first day of classes. So you have access to those. What I want to bring to your attention is that at the bottom of the schedule, which I'm bringing up here, at the bottom of the schedule, there is a collection of problems and their solution immediately after them. So please do not, however, print this document, because even though we have planned the course, so you can see on each day what my plans are for covering and what the homework problems associated with those sections are, things could change. So I may cover less, I may cover more, I may realize that we need an additional problem or two. So this could change. Please don't print it. If it changes, I will immediately update it on Blackboard, so you always have the latest available on Blackboard. So use it as a Blackboard document. The best, I'll get to the slide and explain, but the best way to prepare for this class and succeed in this class is to read ahead of time. So read the sections ahead of time, and this column, second column here, is supposed to tell you what do you need to read before coming to the class. And let me show you quickly where the problems are. Starting from second page, you have homework 1, 2, 3, it keeps going. And you can tell the fact that I have homework 2.1 tells you that this was added later time. Okay. So we did talk about the schedule. The syllabus is also available on Blackboard. I posted it on Blackboard and I emailed it to you. I want to bring to your attention something quickly, that the text is available for free as a PDF, legally available. The authors made it available. There is a print version of the book, but at the same time they made a decision to make it available for free. So please grab that and take advantage of it. The other thing that you're probably curious about is where would your grade come from. So we will have weekly quizzes, and these weekly quizzes will be online to give you and the online section the same questions and the same amount of time and equal way of earning grades. There would be 30% of your entire grade for weekly quizzes on MATLAB, and I'll let you know more about how we'll do those. There would be one midterm and a final exam, each have 35%. Does it add up to 100%? Okay, so there is more explanation. Please take a look at it at a later time if you have any questions on any of the topics. Okay, back to, so we talked about quizzes, how to get ready. If you want print lecture notes, these are what I'm showing you here. I'm going to post them on Blackboard, and I'm going to write on my lecture notes, and I will put that copy also on Blackboard. So most likely there would be two copies, clearly distinct. There is original that has everything that you can see here, and as I annotate right on my slides, I'll also post those. So you get access there. At the end of spring 2016 semester, I gave a survey to students, and I gave them 5 extra points or 10, I don't remember that. But I asked them, what would you recommend to folks coming after you taking this class with me? And this was the end of semester, so they had experienced everything. So they put some comments down, and I selected the ones that there were more details involved and they were more beneficial. And I copied them on this slide. So take a look at it. But if you just quickly browse, you see a few points standing out. They recommend reading the material as I'm recommending before the class to take the most out of the class. And the other major recommendation is, even though the solution to homework problems are available, don't treat this as a reading material. The best way to prepare is, after each class, attempt at solving those homework problems, not reading the homework problems and their solution, because at the first glance, I'm sure you've seen it hundreds of times, at the first glance, the problem seems very, very simple. But unless you sit down and try to solve it, you will not make the mistakes that are essential for learning. Let me repeat. You will not get the chance to make the mistakes that are essential for learning. So you have access to all of that. Please read it. Okay, so as I said, the course has two parts. The first part talks about modeling. And when we talk about modeling, what do we mean? So when I mention the word model, what comes to your mind? Model plane. So what is different between the actual plane and a model plane?
Scaled down.
It's scaled down. So it works like an actual plane without what? What you don't have to do for the model plane that you have to do for the actual plane? You don't have to pay a lot. You don't have to pay a lot to get a model. And that's the key. That's why we bother with models, because you can write mathematical equations that behave the same way or very close to how your actual system works. That was an excellent example. I appreciate it. So that is the meaning of models. So in this class, when we say models, we mean mathematical equations describing the behavior of systems. So the first definition you need to have down is order of models. So again, we established that when we talk about models, we talk about mathematical description of systems, but not all systems are the same and not all models are the same. So one of the first concepts that we are going to discuss is the concept of order of systems. So we talk about first order systems. You can see it here. First order systems. They have special properties. We'll also look at second order systems. But the tools here, the main tool here as a model is one or more than one differential equation. So when we mean model, essentially we're talking about differential equations. Now, who can tell me what is a differential equation? So you can say something I try to avoid my entire life. That's valid. But let's move on. What is a differential equation? What kind of information is in a differential equation? So let's just take one step back. An equation, it basically gives you some information. So x plus y is equal to 2. What information is in there? There is a relationship between how x and y vary, right? That's an equation for a line, by the way, right? So on a plane, you can draw this. So you can see for each value of x, what possible values of y could be. It's a function. It's a line, right? Okay. What is not present in this equation? What is it that we don't have enough of? If you say money, that's not the correct answer. What is the next thing?
Time.
It's time. Excellent answer. So what is not present in that equation of x plus y equals 2, or any other equation of that type, is time. So can you tell me what is a differential equation now? Come on. That involves time. That's it. So one way to look at a differential equation is it gives you that information. Now, do you know of any differential equations? Just quickly off the top of your head. Famous ones? So I'm going to use this tool and see if I can show you a differential equation quickly. So what I'm going to do, this is my first practice. What I'm going to do is I'm going to add blank pages so I can write on these blank pages. So I ask you, can you give me a famous example of a differential equation? And you're thinking, what is the answer? What is the course number for dynamics? It's 2300. That's not my very important, but what is important is have you guys taken it? Dynamics, anybody who hasn't taken dynamics? So what is the goal when you take the course dynamics? At the end of every problem, what are you trying to achieve? What is the end result of every problem in dynamics? Or coming up with equation of motion, right? So what is equation of motion? It basically tells you how the system moves, right? And what is the basic equation? Where do you start for writing equation of motion? What is the fundamental law of physics that you use in order to get to equation of motion? So I'm trying to make sure we are still recording. Yeah, we are still recording. Okay, what is the fundamental law? A guy on the other side of the pond came up with a law. People associated with an apple tree. Newton's law. Newton came up with a law, and I want to repeat that because this is going to be fundamental. Every time we develop a model for a system, we have to have access to some physical law. So all models are based on some sort of physical law. So let me try this guy. So one of the fundamental laws that we will use repeatedly is Newton's second law. And what is that law? It tells you what? It tells you that mass times acceleration is equal to what? Sum of all the forces in the direction of your acceleration. Is it legible? Can you read it, or do you prefer better, maybe heavier text? Let's give that a try. Okay. So every time, so please make a note of that. Every time we need a mathematical model, a model for a system, we need to have a very solid foundation. In other words, we need a law to start with. So if you're talking about a model to describe motion of systems, most likely we'll go to Newton's second law. Now, we established that. I apologize, this also works as a mouse, so we established that. Now, what is this? What is this guy? It is a differential equation. How did you know that? Where did you look to see that this is a differential equation? What gives it out? The double dot. What is the meaning of the double dot? Second derivative with respect to? Okay, so let's just quickly review. So when we have d over dt, it means taking derivative with respect to, if t is time, with respect to time. So dot means taking derivative with respect to time. So single dot, so if we have x here, this becomes x dot. Double dot is second time derivative of x with respect to time. Which means what? Which means you have taken derivative of x once, and arrived at x dot. If you take derivative again, you'll get to double dot. So if x is your variable, so if x is your, let's take another definition down. If x is your state variable, so if x is your state variable, if you take one derivative, you come up with the first time derivative, which tells you how x changes with time. The meaning of x dot is how x changes with time. The meaning of x double dot is what? The meaning of x double dot is how x dot changes with respect to time. Do you follow here? So x dot tells you how x changes with time. X double dot tells you how x dot changes with time. Okay? So these are important definitions. So let me see if I can clean this up so people who are going to read after you don't have to put up with this extra. Okay, a state variable. So we talked about the concept of state variable. State variable in our language, in the language of this class, is the most important variable that we need to know at all times. It's the most important variable that we need to know at all times. So take that definition down, please. So what did we say? The first thing we said was we needed a law of physics. The second thing we said is models would be in the form of differential equation. The third thing we said, we talked about state variables. So we talked about state variables. And this is an example. So this is an example of differential equations in the form. So the law was Newton's second law. The law is expressed in the form of a differential equation, which essentially tells you how x dot changes. What is x dot, basically? Newton's second law gives you x dot. X double dot, which essentially tells you how x dot, velocity of system, changes with time. Now, if you know how velocity of system changes with time, do you also know how position of the system changes with time? That information is built into it. So we'll look at this in more details. But what I want you to know is, even though it appears that it only gives you acceleration, it basically tells you how velocity changes with time, and as a result, how position changes with time. So this gives you all the information you need to predict motion of the system. That's why it's called a model. A model basically tells you how the system behaves. So let's just put it as the fourth main idea of model gives you the behavior. Okay? To make it distinct from every other system, we are going to call systems that we deal with in this class as dynamic systems. Dynamic systems. Now, every system, let's put dynamic for now aside. Every system, the way it's distinguished is by defining what that system is and what causes some change in the system that is called the input. So input is what causes change in the systems. So let me write this. So causes change. So causes change. Input is what causes change. Output is that change. It is the behavior of the system. It's what we're interested in predicting. So output is that behavior. Okay, let's go back to our example. Let's go back to which example did we have? we have Newton's second law. What is Newton's second law? Newton's second law says mx double dot is equal to sum of all forces in x. That defines a system. What is our system in this example? This is model of what? As soon as you answer what, you have defined your system. Do you need more time to think about it? So let's put that aside. So we'll keep it as a question. So I'm going to make a question mark so you know we haven't answered that question. So my question was, what is the model, what is the system that this model is capturing? What is its input and what is its output? So keep that question in mind. Whenever you know the answer, raise your hand and we'll talk about it. But let's move forward. A system could have more than one input. So more than one reason that would cause change in the system. It also could have more than one output. So it's more than one piece of information that we need to know about that system at all times. And we'll talk about those examples. Now, what distinguishes a dynamic system from a non-dynamic system? So what do we call a dynamic system? Now, immediately we go to course dynamics and say, what was the common thread between every system that we discussed in that course? And you said it was motion. But what we mean here by dynamic system is not necessarily motion. There are systems that are motionless, at least they appear to be motionless, but they're still called dynamic system. So what distinguishes a dynamic system from a non-dynamic system? If you look at this input-output behavior, if you look at the fact that a system receives an input and produces an output, if there is delay between input and its effect as output, that system is considered a dynamic system. So you give the system some input, and if the output immediately doesn't change, so there is a delay in change, that defines a system as dynamic system. Okay? I feel that you need some examples, right? Do you? Or you're all set, you don't need any examples? Or it's too early to answer any question, so I see nobody is ready. So maybe we should bring a coffee pot next time. Okay, so we'll work on some examples. But for now, have these definitions. So when we get to examples, I want you to go back to these and see if they make sense. Okay, we already talked about models being mathematical description of systems. Now, whenever we develop a model, we make assumptions. Whenever we develop models, we make assumptions. So the decision of what part of the behavior bring into the equation is a decision which will then define how complex your model will be, right? So again, going back to this model, mx double dot is equal to sum of all the forces. Okay, so when you write an equation, the decision on about what to bring into your model, what forces to include, is part of how valid your model will be. And we'll work on those examples. And this is, the last point is for the next portion of the course when we talk about feedback control. But I want you to be familiar with the concept. When we talk about control, we are talking about changing natural behavior of systems. Changing natural behavior of systems. So what comes to mind is, if you have a mass, and you drop it, what is the natural behavior? It goes down, right? That's the natural behavior. By control, it means that you do something to this system that its natural behavior changes. What is that change? It depends on what you want. But if your desire is that you let this key go and it stays in midair, that is a control problem. So how can you make it possible that I let go of a mass and instead of dropping, it stays? Or even better than that, it goes up and travels. Can we do that? Is it possible? I think we have already solved that problem, haven't we? We made planes. So in planes, what are we doing? We are modifying the natural behavior of that cylinder that we call a plane. The natural behavior of that cylinder is to drop from skies. But through combining sensing, computation, and actuation, we change that natural tendency of that plane to fall off the skies. So that's called control. Make sense? And you can come up with numerous examples of day-to-day examples of control. Another example, the natural tendency of a car, when you put your foot on the gas pedal and push, the natural tendency of that car is to do what? The natural tendency of that car is to crash to the first pole that comes in its way, right? The fact that it doesn't crash means what? Means you're controlling it. By what? By bringing sensing, computation, and actuation to play. Sensing means you see there is a pole coming in. You see a pole, so you do some computation, even though if you don't think about any computation, you're doing some computation, and then what do? As actuation, you take the steering wheel and turn it. That's an example of a control. So that's common in, and to be more accurate, we call this feedback control, and we'll talk more details about it. Okay. So I gave you a lot of definitions. We are going to now look at an example and bring all those definitions into this example and try to make sense of them. So what do you see here? What is this? It's a tank. Is it small? Is it large? Is it a few microns in diameter, or it's few kilometers in diameter, several miles in the diameters? The fact is, we haven't defined. And for our purpose, it doesn't really matter. So we would like to be as general as possible so we can model a dam reservoir as well as an aquarium. But what is the purpose of the model that we are trying to develop here? The purpose is to predict H at all times. What is H? The level of fluid. How much fluid is in the tank is defined by H. Okay, so H is our interest. Do you agree, or something else should be our interest? The fact is, there is no right or wrong answer. We approach this system with this agenda in mind that, okay, I have a reservoir, my boss is paying me to predict how much water is in the reservoir at all time. So my job, my purpose of modeling is to find a model for H. That's why I'm interested in H. If somebody else pays me to determine something else, then my mission changes. For now, my mission is to come up with a model that predicts H, how H changes with time. Okay? So that makes H what? Based on the definitions that we had, and I know you wrote it down. So what is H for us? Absolutely. H is our state variable. Very good. Okay. So the first thing we know is, let me see if I can write it here. H is the state variable. So that's our goal. That's our goal in modeling. Now, when we're done with our model, what will we get as a model? What will be our model? What kind of equation will it be? So we said models are going to be differential equation. So it's going to be a differential equation, and I'm going to tell you ahead of time that differential equation is going to be a first order differential equation. That equation is going to be a first order differential equation, and the main reason for that is the fact that we have only one state variable. So the fact that we have one state variable, so this is just one, determines that this system is order 1 and that we will get one differential equation of first order. So that's so I'm giving you information ahead of time so it can make sense things and develop trends as we go forward. The other definitions we made and we want to bring to this example is the concept of input and the concept of output. This is a very good example to get that down and get more practice on the concept of input and concept of output. Now we said input is what? What was the definition that we gave for input? What causes change in state variable. So if you look closely, what is our system? Our system is this tank. So if I want to separate my system from the rest of the world, I would say this is my system. My interest is in this portion of the world. I've chosen this portion of the world for my study. So that's my system. What causes, and we already determined that our interest is in H. So I want to know H at all times. So that's the purpose of modeling. And H is going to be my state variable. Now, what will cause any change in H? Yes, sir. The flow in and out are going to both affect H. You're absolutely right. But let's decide. Is flow in my input or flow out is my input? Which one is causing the change? The tendency is to say both, and I see that. But let's think this way. If there is no flow in, would there be any flow out? If this tank is empty, without any flow into it, would there be any flow out? So what causes change? Quote, end quote. Cause is flow in, so that's our input. Even flow out is caused by flow in, so that's why there is only one input, and that's flow in. Do you all agree? If not, please challenge me, and let's discuss. Okay, so W in, I keep forgetting, this is our input. This is volumetric flow in. That is our input. Now let's go back to the other definition we made, which was output. Output was what? Should we go back to the definition? Output was the behavior, the change that happens in the system. So what makes sense for us to be output in this example? What behavior are we interested in this system? Absolutely. So H, at the same time as being our state variable, is also our output. So H is also our output. And the general rule is always the output of the system would be state variable. If we have multiple state variables, sometimes the output is one of the state variables. So the general rule is, always output is a subset of state variables. So in this case, we have just one state variable, and that will also be our output. Okay, so we discussed the model a lot, but what haven't we done? We haven't actually created the model, have we? No, we haven't created the model. Okay, so in order to create the model, I said we need a fundamental law to start with. So what is the fundamental law that determine the behavior of the system? So when you think about the system, what should always be true? What should always be true will be your law. Do you see that? What is the fundamental truth that we can just always go back and say, this is always true about this system? So while you think about it, let me redraw the system in the corner. So fundamental law. You know the law. I'm sure you know. Yes, sir. Okay. Can you repeat it one more time?
Conservation of mass.
Okay. So you're saying this system is no magic system. So mass that comes in either stay in here or goes out. Okay. Do you all see? Do you all agree? So it's going to be conservation, the law. Okay. Because we are dealing with liquid, can I convert that to volume? It probably makes more sense, because if I don't convert it to volume, then I need to keep track of the mass, which means I have to do a bit more calculation. So I'm going to write the law. The law would be, the law would be this. Let me see if I can capture what you say. I would say change in V, which is volume, is going to be what? It's going to be equal to what? Change in volume is what? Volume of what, by the way? What? Volume of fluid in this tank. Change of volume of fluid in this tank is equal to what? It's equal to?
V minus V out.
Yeah, V coming in minus V going out. So we can say V in minus V out. So that's our law. That's our fundamental law that we are going to use to arrive at our model. Okay, so what is Vn? Vn, we already have it. We have called it already Wn. It's just a choice for variable. We could call it anything, but because we have called that volumetric flow n Wn, I'm going to use that variable. Now, what is the flow out? How much fluid will go out of this tank? Do we know? We don't know. But let's just do some experiments with this tank to determine. If this tank is empty and Wn is 0, what is the volume going out? 0. So, so we determined something. If I close this, if I close the orifice at the bottom of the tank, how much fluid will go out? 0. So if I open this orifice a little bit, how much fluid will go out? A little bit, right? If I open it more fluid will go out. So it has to do with how much opening I have at the bottom. So I have to capture the amount of opening somehow. So two things so far. One is, if there is no fluid in the tank, no fluid obviously goes out. So it has to do with H. If we have more H, more fluid will go out. And if the opening is more, also more fluid will go out. Do you see? Okay, are we ready to put something down? I think we are. So we are going to make an assumption that the volume out is going to be proportional to H. So I'm going to write H. And the constant of proportionality is going to be simply a constant. I'm going to write it as C. Okay? And where did we get that? Based on some experiments. So we said, as we put more fluid in the tank, more volume will go out, and as we open this orifice more, so we are going to capture that effect with that constant. So if we have a large orifice, C would be a large number. If we have a small valve at the bottom of the tank, C is going to be a small number. Do you see that? So that's why anytime we have any opening at the bottom of a tank, we are going to define it with variable C. So we are going to C of this orifice is this much. So we know what kind of, how much fluid are we going to lose through that opening. Okay? So we have looked at the right side of this equation. Let's look at the left side of the equation. What is change in V? How can I mathematically write that down?
V dot.
Say it again.
V dot.
V out, did you say?
No, V dot.
Oh, absolutely. Yes, yes. With time derivative. With time derivative means just that. So we are going to write it as either V dot, or if you want to give more information, you're going to write it as dV over dt. So time derivative of volume of fluid. Okay. So everything is set. Are we done with our model? The only problem I see is that I said my state variable is going to be H. So I want to know how H changes with time, but what you've given me is how V changes with time. Okay, so do you see what is missing? So I want to know how H changes with time, my state variable, how it changes with time. But what you have given me is how V changes with time. So we need to do a little bit of work. How can I bring H into this equation?
Volume is area times height.
Absolutely. So if I know area of this tank, call it A, then I know volume is going to be A times H. So dV over dt is going to be d of AH over dt. Now, what is the time derivative of A? How does A change with time? The answer is it doesn't. So it's not a time-dependent variable. So what I'm going to do is pull it out, write it next to dH over dt, and that is equal to Wn minus C times H. Or I can write it as H dot is equal to 1 over A times Wn minus CH. So what does this tell? This is a model for our system. This is the model, by the way. That's the model we were after. So this equation tells me the way H changes with time is this. The way H changes with time is that. Now, let's take a closer look at this model and see if we can determine how really H changes with time. So let's assume at the beginning the tank is empty, which means what? Tank is empty means H is 0. And then you have a valve at the top of this tank and you turn it 1/4 of a turn and you let a constant volume of flow to start flowing in this tank. Okay? Which means what? Which means Wn is going to be a constant but positive value. Okay? What that constant positive value will cause, according to the model? Look at the model. We need to tell the story now based on the model. So we have Wn that is non-zero. H is 0, which means this, when H is 0, which it will mean this portion at the beginning is not going to show up in the model. It's not going to contribute to the model. But this is non-zero, which means what? As the result of this input, what will happen? You will have a non-zero H dot. At what rate? Value of H dot would be Wn divided by A. So A plays a role in determining what? A plays a role in determining dot. So A plays a role in determining how fast this tank will fill up. Can you relate to that? Of course you can. If you have a large aquarium and you have the same hose going to it compared to a small container of water, the first one will fill much slower. The reason now you know based on your model is because you have a large cross-section area. Okay, so the first piece of information that you're getting from the model is that the cross-section area determine the speed of the system. The speed of the system is determined by cross-section area. Now, as soon as the tanks start filling up, H is going to be more than 0. So H is going to be more than 0. So this portion, this is going to be more than 0. Okay? Now, the level starts rising. Rises, rises, rises. And what eventually will happen? Will it rise indefinitely? We know from experience that this can't happen. It will not rise indefinitely. But what will happen that will stop the level to rise? Can you speak in terms of my model? I've invested a lot of time in my model, so I'm very attached to this model. You're on the right path, but look at the model. So we know based on experience at some point H stops changing. Do we agree? So in terms of modeling language, H stops changing means what? Stops changing means that's the meaning, but mathematically stops changing means what is 0? H dot is 0. Stops changing means H dot is 0. Don't you see that? Okay. H dot means equals 0 in our model means what? Means the level has reached to a point where Wn is equal to Ch. Do you see that? So there is a specific H. At that point, Wn is equal to C times H. So and at that point, H dot will get equal to 0. Now what happens after that? H dot is 0, H is not changing, means what? Means the level of tank remains stationary. So far as Wn is constant, the level will remain stationary. So the same amount of fluid coming in leaves the tank. And that's the meaning of Wn being equal to CH. Okay, so here's my challenge. I want you to grab your pencil or pen and put it on the paper and plot H versus time. How will H change versus time? How is H a function of time? Okay? So tell me, show me the picture. So tell me how it will behave. I can see your picture, but explain to me.
It starts off increasing, but over time as it reaches that point where Wn equals CH.
So you have like a ramp which levels off. Okay? Any other picture that you guys drew? Okay, so what if I heard him correctly, he says at 0 it's 0 and it gradually goes up and then levels off here. Okay, that is exactly what happens. So the challenge I have is if I touch this, it thinks that I want to move this. So this is how it behaves. So it will level off at some point, and this is basically extends to 0. So I can do this. So it starts from 0. At time 0, it's 0. And it actually does level up. So I need to correct this. So it doesn't keep going indefinitely. So at some point, it basically levels off. So it becomes a line. Okay. Can you calculate that level? So if we call this level that, by the way, I heard the word equilibrium, and it's absolutely correct. This is the equilibrium. What equals what? Input equals output. What comes into the system is equal to what goes out of the system. So we can calculate this equilibrium point. How can we calculate it based on our model? We said at this point, what is happening from the model? We said in the model, at this point, H dot is equal to 0. So we take that into our model, which tells me that this is equal to 1 over A Wn minus C, that specific value of H, which I'm going to call H naught. So if H is equal to H naught, H dot is going to be equal to 0. And from here, I will find H naught to be equal to Wn divided by A times C. So basically this tells you the smaller the orifice, what is the consequence? He said C defines how small or large the orifice is. Smaller value of C means smaller orifice. So a smaller opening at the bottom of this tank means what in terms of H naught? A higher equilibrium. Can you see that? A higher equilibrium is caused by a smaller orifice at the bottom. But does it make sense that cross-section area also have anything to do with the equilibrium? In my solution, cross-section area is at the bottom. So basically, if a tank is larger, the equilibrium should be higher. Does that make sense? I need your help, guys. It doesn't make sense to me. So tell me why we have A in the denominator here. Because mathematically, I see A is in the denominator, but cross-section area has nothing to do with where we reach equilibrium. I can relate it to the orifice, but I have a hard time relating it to cross-section area. So if the tank is larger, it will go higher. That's what the story tells. This tells. If the tank is larger, the level of tank would be higher. But why? So when you arrive at a point like this, you have two solutions. Either you have to come up with an explanation, or you have to go back through your calculations and see if you have made a mistake. So let's try both of them. I failed at the first route. Now see if I made a mistake in my calculation. Did I? Yes, sir. As simple as that. I made a math calculation, guys. Wake up. I did make a math error. A doesn't show up in CH because the other side is 0. If you multiply both sides by A goes away. So Wn is simply equal to what? Equals? Let me see if I can erase this very elegantly. It's Wn over C. That's it. So in this very simple example, we came with a few very powerful ideas. It may not be apparent how powerful they are. One is we determine the equilibrium. The other one is we determine how fast this system is, and we determine what determines the speed of the system. You remember that? What determined the speed of the system? The speed of system was determined by this guy, by 1 over A. And the equilibrium was determined by 1 over C. So these are the type of trends that is going to be helpful in actually designing the desired behavior later on. When we get to control, normally we try to reach a certain speed in the system. We try to change the equilibrium for the system. And it's very important for us to know how to find them before we start changing them. We need to know the actual value before we go to change them. Okay, so why don't we take a 5-minute break and we'll continue after that. Does that work, or you just want to go straight? Break, no break, doesn't matter, or does matter? I'm ready to go. Would you like to go? Okay. All right. So we talked about this example. Let's just review. We determined the state variable ahead of time. We determined the input to the system. We determined the output of the system. Then we went to the law that we knew it was going to hold always, and basically wrote that law in math language. And that gives us the model. And then we went ahead and determined, based on what we see in the model, what kind of behavior will the system have. And we determined the speed of response. We determined the equilibrium. Okay. Now, this plot that I have It's just one of the possible behaviors of the system. Don't you agree? So what is another possible behavior? Another possible behavior is this. Let me give you the initial condition and you can tell me what will happen. What if the tank, before we start the flow in, the tank is already full. To what level? Let's say it's full to this level. Ah, I'm sorry, I have the eraser. Okay, so to distinguish it, let me change the color. Let's say the tank is full this much. Not a good choice. The tank is full this much. So what if the tank is full that much? Again, your challenge is to grab your pencil. I know it's very hard sometimes. Grab your pencil and draw the response. What would be the response of this system? So the only thing we are changing is that initial value of H, initial condition. We are not changing anything else. We are not changing A, we are not changing C, and we are not changing Wn, how much fluid is coming to the tank. So we keep it as a constant. So for this case, Wn is constant. Okay, who has the response? If you had it, raise your hand and I'll ask you to explain it to me. Yes. How will my response look like?
T equals 0, it'll start at your initial height,
Okay.
and then it'll just have the same general shape and increase until the equilibrium.
Okay. And where will it settle? What would be my equilibrium position or point? We have three choices here. Would my equilibrium be lower than H naught? Would be exactly the same as H naught, or would be higher than H naught? We covered all possibilities, right? So which one would be the case? Yes.
What does it say?
Why do you say that?
The ratio is not changing. One over C or one over A.
Because we found an equation for H naught, and in that equation there is no place for initial condition. It simply says if your Wn remains the same, your H naught remains the same. Can everybody see that? So in other words, if I want to draw this, it will start from this point and simply go to this exact same equilibrium. I apologize. I can't quite touch this because as soon as I touch it, it starts modifying it. But that plot actually starts at time equal to 0. It starts at the point. So let me see if I can do this trick and move it. So you see the image. So it starts from that point and goes up. So let me give you another initial condition. What if the initial condition was here? How will my response look like? I know you know the answer, just say it. How will it look like? Yes. Absolutely. So it starts from that point, but it decreases. Now, is all of that predictable by our model? Let's take a look at our model. So we know what H naught is, and we have an initial condition that is more than H naught, the equilibrium. Do you see that? In the last initial condition that I gave you, that's more than the equilibrium. So what will happen? If you look at the model, this CH is more than Wn. Look at it. Because H is more than H naught, CH is more than WN, which means what? Which means this is going to become negative. Do you see that? So this becomes negative, which means what? Which means H has to decrease. So what is happening is predictable. Our model actually predicts that. So if you have an initial condition that puts you here, you would start and you go that. Now, my hand is not, so this drawing is not smooth, but the behavior is smooth. So it just smoothly goes down. So I was hoping that Adobe would smooth this out, but it didn't smooth it out. But it basically goes down, and the end result is exactly at H naught. Now, here's the more interesting case. What if your initial condition is exactly on H naught? What will happen? So the tank is filled to the level that is equal to equilibrium. What will happen? Nothing. So you have set it such that the flow coming in is already equal to flow going out. So if you fill the tank to H naught and then open the valve to Wn, which is the constant level, it just stays there. So that's the last possibility. Okay. So hopefully, so what I'm trying for you to get out of this is to see the trends. Where do we start when we want a model? What is it that we can get out of the model? So what I want you to develop over time is to dig into your model. Don't be afraid of a differential equation. So when you see the differential equation, approach it. Try to look at it from different angles. Try to get as much information from it as possible. See what we did with a simple equation? It's a simple equation, isn't it? H dot is equal to 1 over A Wn minus CH. So we calculated many different things from it. We established the speed of the system. How is it determined? We established equilibrium. We looked at various possible behaviors, and we determined all of that from this simple equation. So that's the power of having a model without ever building a tank. So that's it. So you can predict what a tank behaves without ever making it. Now, let me set something straight here. We are not looking at a tank because tank is inherently a very important system. We look at the tank because we have a feel for the tank. You know how this system behaves. So you can relate your feelings, your understanding to mathematics. So you can go back and forth. Now, once you establish that, then you can think and generalize it with systems that are not as accessible to us. So what if I have a circuit here? I'll show you a circuit, hopefully today, that behaves like a tank. Why it behaves like a tank? Because its differential equation looks like a tank. There we don't have flow in and height. There we have voltage and current. Okay. I want you to gain that confidence and basically don't be afraid of systems. So this is our second example. It's a mechanical system. Input is the force that the engine puts into this system. So it pushes it forward. The result of the engine and interaction with the road, everything is just, we simplified as a force pushing this forward. And that's it's a very good point to talk about simplifications and assumptions. So you have a choice what to include in your mathematical model. What is it that interests you, and that determines how simple or complex your model should be. Now, if you think about a modeling of a car, you can write thousands upon thousands lines of code to capture the behavior of a car. If you want to be predicting, for example, how a cooling system in a car works, or if you want to know exactly how friction in a car works, how the interaction of tire and road work. So you can have very complex models, and in order to simulate it, you can have thousands of lines of code, and there's commercial software out there that does that, right? You're familiar with that concept. more or less. Or you can have code that simulates the engine, how mixture of air and fuel or the speed of or pressure of injection would affect the performance of the car. So that can also be modeled. Now for now, we are going to go very, very simple and say, I really don't care how the torque is generated. I don't really care about how a tire interacts with the road. I'm going to just want to know how the car will speed up. What is the velocity of the car at each time, given that I know how much force is pushing the car forward? Do you see how much simplification is going to that? But that's okay, because that's what our interest is. So there is no right or wrong model. That's another thing that I want to engrave in your brain, that there is no right or wrong model. It's just our interest. Today we are interested in simply relating the force that pushes the car forward to its speed. Okay? So our input is the force, output is velocity. We need a model to relate input and output, and we need, of course, a differential equation. So this is your challenge. I want you to think about it. How are you going to model that? What is the basic law that you start with that has the force in it and has velocity in it? So think about it for a minute, and I'll ask you to give me the answer. So what law would give you velocity and force in one equation? You can explain it, you can give me formula, whatever. Newton's second law, yeah. In every time we have motion, Newton's second law is the fundamental law. So what does Newton's second law say? Newton's second law says, before doing anything, you need to do what? You need to draw a free body diagram. My apology. I should have silenced this ahead of time. Okay, so whenever you have a motion-related system, you start by drawing free body diagram. What is free body diagram? Quickly to review for all of us, is what?
Summation of all forces acting on the object.
Yeah. So what do you include? Whatever has inertia, you include, and you take away everything else, and you put it as force or forces, right? So here I have this car that has a mass of m. And the only force that I'm going to include is this force F that is pushing it forward. And we also have this variable X, which is going to be a function of time, that determines its position. Now, our interest in this example has nothing to do with position of the car. I'm interested in what? I'm interested in velocity, which tells you what, by the way, ahead of time. What is the state variable? Velocity. So state variable, so let's write it down. State variable is v of t. And so is the output of the system. Please remember that general rule. That output is one, or a subset of state variables. We have just one, so it makes sense immediately that the output is my state variable. Okay, what does the law say? Newton's second law. What does it say? Okay, so let's go here to the next page. It says m times a is equal to sum of all forces, which in this case is F. Now, speaking of simplifications and assumptions, in my free body diagram, I didn't put any force that was opposing this motion. But in reality, there are forces that would oppose the car going forward. Can you name one? The weight generally is pulling the car down, but indirectly slows the car down. How does it indirectly slows the car down? The weight through friction. Through friction. So that's one force that would be opposing the motion forward. What is the other force? The drag, which has to do with the shape of the car. Okay, so to simplify, let's just do this. Let's put a force that is opposing the motion and call it lowercase f. Lowercase f. And lowercase f, let's just include the force of drag for now. Are you here for modeling and control? Is there another class starting here? What time?
It's 9:50.
9:50. Okay, so we'll. Oh, no problem. Okay, so when we go to Newton's second law, we have the force pushing the car forward minus F, which is the force pulling the car backward. And the reason it has minus is because of the direction. So look back at the free body diagram one more time. So capital F is in the direction of what we consider positive motion. So it's in the direction of x positive. But lowercase f is in the opposite direction. It's in the opposite direction, and that's why when it comes to writing Newton's second law, the lowercase f appears with a negative sign. Clear, everybody? So let's make another assumption to make our lives easier. We are making the assumption, so let's assume that lowercase f is proportional to the speed of car. So c times v. So the faster we travel, the more drag we'll have. That's what essentially we are assuming. Now, is this assumption correct? You have a general feeling that the faster you move, the more drag you have, but this, you need to do experiments. You need to go in the lab, in the wind tunnel, and measure the actual force. It would have to do with the shape of the car and other variables. But this is a simple assumption we are making. We are saying it's just related to speed linearly. Okay, so let's go forward with our model. So this is m times, what is a? A is dv over dt. And the reason we're doing that is because our interest is in predicting velocity, how velocity changes with time. That's why we are converting v to a rather to dv over dt. So dv over dt is equal to f, which is the force of engine, minus c times v. Or you can write it as dv over dt, or v dot, as 1 over m times f minus cv. Now, what I want to bring to your attention is this. You remember the model that we developed for the tank? Do you remember that? If not, look at your notes. Wasn't that h dot equals 1 over a wn minus c times h? Do you see any similarity? Even though those systems couldn't be farther apart from in appearance, in function, or how we feel about them, yet their mathematical model is very similar. So what does that mean? So what does that mean? Yes. It means a lot of what we learn about the behavior applies here. It applies here. So, for example, if you start your car at zero velocity, under a constant level of force, can you predict how change of velocity will look like? The plot? It would look like exactly the same as it appeared for the tank. So why don't you go ahead and plot that? So we can talk about an equilibrium velocity. We can calculate that equilibrium velocity. Exactly the same approach. How do we calculate equilibrium velocity here? What does it mean, equilibrium? It means the car is not accelerating anymore. So it had reached a constant velocity. And that constant velocity would be what? What is the value of constant velocity? So if you put v dot equals 0, we'll find v naught to be equal to f over c. F over c. F over c. So the more drag the car experiences, the slower that equilibrium velocity will be, because c determines the strength of drag force. So the larger the c, which means more drag, the lower that equilibrium velocity would be under the same effective engine. So if you put a certain engine in the car, the maximum or equilibrium velocity it can get would be lower than if you basically reshape the car so the drag would be less, so the equilibrium velocity would be more. And also you can see how fast the speed changes. So how fast does the speed change? What determines the acceleration rate? Look at the model. What determines the acceleration rate? So assume at the beginning v is equal to 0. So you start revving the car up, you get to a constant force, and let the car go. So what determines the rate of change of velocity? Mass. Doesn't that make sense? That the mass determines how fast the car accelerates, how fast the velocity changes, basically. And that's the essence of Newton's second law. So the third system that we are going to look at today is a heat transfer system. So what does this look like? So it will be, assume that it looks like this. So we have an insulated space. There is a heating element here, and it puts in a heat flow. So let's call this Q in. That's the flow of heat that this heating element puts in. Okay? So what is our interest? Our interest is in predicting the temperature of this space. We are controlling the temperature. It could be this room. It could be a building. It could be a tiny vessel. It could be a large stadium that we're trying to control the temperature. So there is a variable, T. And this variable is our what variable? State variable. And by the way, it is also our output. That is the behavior that we are interested in. Now, of course, the outside would have another temperature, T infinity. And we need a model. So what is the basic law of physics that would determine our model? So we talked about conservation of mass or volume. We talked about, by the way, you know that Newton's second law is conservation of what? It's conservation of linear momentum, guys. So we need now another conservation law, probably. What is that? Conservation of energy. So energy in, energy out is equal to change in energy. Okay. Oops. Let's add. I need to go here. Add a page, so we can write our equation. So let's look at the law. It basically says Qn, which is heat energy in, minus Q out, is equal to change in energy. And we know that it is going to be equal to mass of the fluid inside times heat capacity C times rate of change of temperature. So Qn is an input. So you don't know it, we keep it as a variable. How about Q out? We need to make an assumption. We need to assume the mechanism for heat transfer from inside to outside. So let's make that assumption that Q out, so we lose heat through convection. So it's equal to convection coefficient H, cross-section area or area that is in touch with the surrounding, times the difference in net temperature, so T minus T infinity. That tells you if temperature inside is higher than the temperature outside, you're going to lose heat to outside through the area and through the constant that defines the amount of convection. Okay? And we are going to define a new variable, and that's a trick to simplify the model. And that new variable is this. So we are going to call net difference between temperature of inside and outside as a new variable. Let's call it theta. So theta is the net difference between temperature of inside and temperature of outside. If we make the assumption that temperature of outside is constant, then dt over dt, change of temperature of inside, is going to be equal to d theta over d. Can you see that? So if temperature of outside is constant, then the time derivative of temperature of inside is equal to time derivative of theta. Okay, so that brings us to substituting for Q out. So we have Q in minus Q out would be what? Q out would be H times A times what? What did we call T minus T infinity? Theta. So it would be HA times theta. It is equal to MC times d theta over dt. Or we can rewrite this equation as d theta over dt equals 1 over m times c times q in minus h times a times theta. Do you remember that for the tank we had h dot equals 1 over a wn minus c times h? Do you see any similarities? Again, time derivative of a state variable is equal to 1 over a constant. M is a constant, C is a constant, so when you multiply them, they're still a constant, times the input that causes the change, minus a constant times a state variable. Do you see that? Oh, we will be done in a couple of... You start at 9:50?
9:50, yeah, but we have our LCC students waiting.
Okay, so we'll finish right away. Thank you. Okay, so let's wrap up. So we started by a law of physics. We started by determining how to apply that law of physics. We determined this state variable, we determined the input, we determined the output, and we put them together. And what we strive to do is to use these generalities. So look at the type of the model and be able to tell a lot based on these generalities. Okay, thank you very much. Sorry about the initial late start. Now we know where we meet. If that changes, I'll let you know. Thank you.